All right, mathletes, here we are looking at similar triangles. So when we think about similarity with shapes and here in geometry, think about an object shrinking and growing in proportion. So if we're looking at a picture here, if we shrink and grow this in proportion, we know that the image is never distorted. That if I make it larger, it's the same proportion and it looks realistic as it was in the original state it was. I can make it smaller and it's still all in proportion to the original size that it was at. Okay, but when we aren't doing things that's similar, notice if we shrink and grow and things get out of proportion, no longer are these objects similar. That this image of this ram looks very different when we have it in or out of proportion. So what we're going to be talking today is about looking at triangles and how do we know when triangles are similar? What kind of theorems can we establish to know if triangles are similar? Because if we look at that triangle and we duplicate it, okay, we know that these two triangles would be similar if one was smaller, one was larger. But how do we know and determine when they're not similar so that they're not in proportion? Okay, so our goal today is to talk about these theorems to prove triangles similar. Notice it's going to look similar to proving triangles congruent, and that's what we want to be careful of is we don't get confused with those. So notice as we're proving triangles similar today, we have a new one to the batch, angle-angle similarity, which wasn't able to prove triangles congruent because we didn't have any sides. But as long as we have angles with triangles, that's going to be sufficient. This one, side angle side, shows up again. It looks a little bit different, um, where our sides don't have to be congruent, but in proportion. And then again, SSS works as well. So notice also what's important, what's not there. What doesn't work to prove triangles congruent? Well, again, our SSA doesn't work. Okay. And we also had, well, notice if we have angle, angle, side, that does have angle, angle. So that's kind of embedded in here as well. Okay. Also, we talked about angle, side angle. Okay. Again, notice it has two angles. So that one kind of works again here with angle, angle similar. All right, let's go ahead and look at the um, theorems that we use to prove triangles congruent. So here, in the first example, we said, okay, we had a side, 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 side. So by side, 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 we were able to try it and say the triangles were congruent. Here, we had an angle in between a side that we knew and another side that we knew. So by side, angle, side, we were able to prove those triangles congruent. Okay. And then in the last example, we see that we have an angle that's congruent to this angle, and a side, which is congruent to this side, and an angle congruent to this angle. So this was by angle, side, angle congruency. Okay? So yeah, remember that was the symbol for congruent. Okay? So now we're going to be looking at similar. Notice the notation with similarity. It's this squiggly line there. Okay, tilde. And so ways that we can prove triangles congruent. These are our theorems, ones that we need to know. So we have angle-angle postulate. If two triangles share the same angle, by default, we know they share the third angle as well, because if three angles add up to 180 degrees, and we know angle 1 and angle 2, then this third missing angle for both of them would have to be the same. So if we know that two angles of a triangle are congruent to two angles of another triangle, then the triangles are similar. Okay, so as long as we have two angles, we know that triangles are similar. Okay, our next theorem is side angle side theorem. If an angle of a triangle is congruent to another angle in the second triangle, and the sides including the two angles are proportional. So notice they don't need to be congruent now with similarity. They need to be proportional. Okay, so when we think about proportional, we should think kind of fractions. Okay, so to show that these triangles are similar, Okay, but we can see that these angles are congruent. So we have our angle here. Okay. To show that sides are proportional, okay, we have to show that the proportions are the same. So I'm going to call this the small side. This is a large side. So if I have a proportion of, let's just do small over large. Okay, small over large for this triangle is 12 over 15. So anything that holds this proportion is true. So remember, proportions we can reduce because we're scaling, we're making things larger and smaller. So if I reduce this, okay, and we reduce them for both triangles, if the reduced fraction is the same, then we know they're in proportion. So 12/15ths, they both have a factor of 3 that goes into them. So 3 goes into 12 4 times, 3 goes into 15 5 times, and 4/5 is a reduced fraction. Okay, so if I look at the triangle over here, I recognize the small side and the large side. So my proportion is small over large, so 8 over 10. They both have a factor of 2 in them, so 8/10 is the same thing as 4/5. And so since we can reduce these fractions to be equivalent, okay, then they are proportional, and therefore these triangles are similar. Okay. Our next is with side-side-side theorem. Okay, so with side-side-side theorem, we want to make sure all sides are proportional. So sometimes we can do proportions within one triangle, small to large like we did in the previous example, and sometimes we can do the proportion for the sides between across triangles. So as I'm thinking about this, I can think about, well, I can call this my big triangle. I'm going to call this my small triangle. So now if I set a proportion of small over big, okay, I'm going to now set up proportions based upon the sides. So these are small triangle, big triangle, and now we're going to talk about sides. So we're going to have sides, so the smallest, so sides, I'm just going to say sides 1 for smallest, sides 2 for the medium size of our sides of our triangle, and side 3 for our largest. Okay, so if I look at the proportions here, okay, for my small side triangle, the smallest side is 2. Okay, so small side 2. For this triangle, the big is 4. Okay, for my medium-sized triangle, or the medium sides, that's 6 and 3. So then I do small over large. Okay. And then my largest side, my small triangle, is 4.5 over 9. Okay. Notice that all of these fractions, 2/4 can be reduced to 1/2, 3/6 can be reduced to 1/2, and 4.5 over 9 can be reduced to 1/2. So all our sides are in proportion. So yes, these triangles are similar. So we need to be able to show the proportionality of the sides in order to be able to conclude that they are proportional. So make sure you look at all 3 sides for the side-side-side theorem. Okay. So let's look at an example. So how can we show the indicated triangles are similar? Okay. So notice with these similarity statements, just like our congruence statements, the order is really important. So we know that S is corresponding to P because they're in the same order. That R corresponds to R, or to N as well. Okay, and T corresponds to Q. Okay, so if these triangles are proportional, well, I only have an angle that I know is congruent. So that doesn't work without knowing these other 2 angles. I can't use angle-angle similarity. So that means I only have 2 other things in my pocket. That's side-angle-side and side-side-side. Again, I don't have all three sides, so I'm missing this hypotenuse here, so I can't use that, so I want to use side angle side. Well, I have my angle in the middle, two sides we know, so that's checked off there. So I need to show the sides are in proportion. So if I do my sides in proportion, so maybe I do the small triangle over my large one. So this is our small, this is our large. So if I do side SR, oop, that's not SR, SR is in my large triangle. Let's make sure, you, again, setting up your fractions are going to be important here. So for my large triangle, my left side, SR, is 24. So SR is up here, so my corresponding side is PN, so PN's here for my small triangle, that's 18 over 24. Those both have a factor of 6 in them, so that reduces to 3/4. Okay, so now for my next side to test, my large side are 28, so I get 28 over, so RT corresponds to NQ, which is 21. 21 and 28, if you're a football fan, you know they're divisible by 7. So 21 has 3 touchdowns. 28 has 4 touchdowns. Okay, or factors. So since they both reduce to 3/4, it's proportional. So we know by side angle side similarity. Okay, so for my next triangle, okay, looks like I have all the different sides that I need in proportion. Or all my different, I have all 3 sides, so I'm thinking I'm going to be using side similarity, but I need to make sure that I set this up right. So I'm going to call my small triangle, hang on, okay, and my large triangle, this blue one. Okay, so now let's go through side 1, being the smallest side, then side 2, and side 3, and let's see if these proportions are equivalent. So for my small triangle, the one in the green, my smallest side's 9. Sometimes it's easier just to stick with one triangle and set them all the way across. So my next largest side is 12. My next largest side is 15, or the largest side. That's all for my small triangle. Now for my large triangle, the one in the blue, okay, my smallest side is 12, and my next size is 16. My next largest side is 20. Okay, so now as I look at these fractions, are they equivalent? Okay, so 9 over 12 divisible by 3 on both of them, so I get 3/4. 12 over 16 divisible by 4 on both of them, so that gets 3/4. 15 and 20, that's divisible by 5, so that gives me 3/4. So all sides are proportional, so therefore by side similarity, I can determine that they are similar. So again, same sort of question. Explain our reasoning. Well, I don't have any side lengths, so the only thing I'm thinking I can use is angle similarity. Okay. Well, I know I have one angle that's similar or congruent, so that's good. Well, let's test with 2 angles in a triangle. I know I can find that third angle. So that third angle is going to be 180 minus 90 minus 26, which is equal to 64. And using the same logic, we're going to see that this angle over here is 26. Okay, so we can determine the triangles are similar by angle similarity. Okay, and now I need to write my similarity statement. So triangle So I'm going to work on the left one. C, D, E is similar. And now I need to make sure my corresponding parts. So since I started with C, it's angle of 26. My angle of 26 is from the triangle angle K. And D is my right angle. So my right angle of my other triangle is G. Okay. And my E angle is my last one, 64, which is H on this triangle over here. Okay. Example 3, show that the two triangles are similar. So notice that ABE is this top triangle here. Okay. And triangle ACD is there. And since they both share this common angle up here of A being equal, and they share this common angle of 52 being equal, okay, by angle similarity, the triangles are similar. Okay. On option B here, we're looking at SVR and triangle UVT. So notice we have parallel lines. So with parallel lines, I have transversal. And I know that alternate interior angles are congruent. My second transversal is here. So I have alternate interior angles being congruent. And since I have two angles of the triangle being congruent by angle similarity, I know that this is true. Okay, 4, show that these triangles are similar. So write a similarity statement. Well, here, again, I have at least two angles being similar. These are equilateral triangles. And equilateral are equal angular triangles. And equal angular triangles, if they all have equal angles, then they're always all equal lateral equal angular triangles are going to be similar to one another. Okay, so as I write my similarity statement, it doesn't really matter because of the rotational symmetry that works within our equilateral triangle. So FGH is really similar since all the angles are the same. It doesn't really matter what I'm going to do. I'm just going to write it as it's written above R, Q, and S. Okay, but that's our similarity statement there, making sure you put your triangles to identify what you're talking about, and then having your symbol there. Okay, so show the triangles are similar. So again, I'm looking at this triangle here. I know that this angle is 32. This angle is going to have to be 58 to add up to 180 degrees. And with that same logic, that this angle, for this triangle over here, DEF, this angle here's got to be 32. And then this is a right angle. So by angle, I have similarity here. And so if I write my similarity statement, I have triangle CDF is similar to triangle. So C is 32, D is 32. D is 58 for my blue triangle. 58 is E here. And so then it is F corresponds to F. Okay. Example 5 here. Which of the three triangles are similar? Write a similarity statement. So I'm looking for that common proportionality here to try and determine which triangles are going to be similar and finding that common proportionality here. So for me, it's going to be easiest to kind of color code them. So I'm going to use this as my red triangle. This one's at my green triangle. And this one's at my blue triangle. So what I'm just going to do is I'm going to pick two sides of the triangles and set up proportions. So I'm just going to say small side over large side. So if they are similar, they have to have this ratio being the same. So for my red triangle, my smallest side is 20. And my largest side is 26. So they're both divisible by 2, so I get 10 over 13. Okay, for my green triangle, I'm going to look for my smallest side. So my smallest side is 24. My largest side is 33. Okay, 24 and 33 are relatively prime, so that can't be simplified. So those can't be similar there. For my blue triangle, if I look for my smallest side, I'm going to get 30. My largest side is going to be 39. And 30 and 39 is divisible by 3, so I get 10 over 13. So then I see that these two fractions, the red one and the blue one, have similar proportions, so they are similar triangles. We got two sides in proportion. We could check the third side, the medium side, that's 24 and 30. Okay. And so if we look at those, they are also going to be in proportion there. Okay. So if we write our similarity statement, I'm going to say that triangle, let's just start at the small side. So that's L, M, N is going to be similar to triangle. Small side is Y, Z, X. Okay. Next example here. Final example, find the value of X that makes this triangle similar. Okay, so for these to be similar, we got to think about our proportions. So what I look for is my key. So my key is the side that I know for both of them. Okay, well, AB on this triangle is 4, and then I know DF, DE is 12, so there's my key. So I know that everything from this triangle to this triangle, okay, that it's times 3. Okay, so this triangle, the side lengths are 3 times larger. So in order to solve for X, I can use this proportionality here and say that I know that 3 times my side BC is going to be equal to EF. Okay, and that's going to be true. The scale factor is going to be true for all of them. Okay, so if I want to find the value of X that makes this true, I can do some substitution. So I get 3 times X minus 1 equals 18. So now I can solve that out, and I get 3x minus 3, distribution property of equality. Add 3 to both sides. And I get 3x equals 21. Divide by 3, divide by 3, you get x equals 7. Okay. So now let's make sure that's a reasonable answer. So I plug in 7 here. 7 minus 1 is 6. Okay. If I plug in 7 here, okay, 7 plus 1 is 8. 8 times 3 is 24. So to check my work, I see that these two sides should be half of each other. So DE is half of DF. Do I notice that's true for this triangle? Is 4 half of 8? Check. So sure, X being 7 satisfies that. That concludes our notes today. Please highlight any questions and bring them to office hours.